SCITECHTALK with science breaking news. Scientists struggle to stay grounded after a possible gravitational wave signal. Today, Wednesday, January the 13th, 2016, here live on SCITECHTALK Science Channel. Scientists struggle to stay grounded after possible gravitational wave signal. Not for the first time, the world of physics is abuzz with rumors that gravitational waves have been detected by scientists in the United States. Krauss, a cosmologist at Arizona State University, tweeted that he had received independent confirmation of a rumor that has been in circulation for months, adding, "Gravitational waves have been discovered." The excitement centers on a long-standing experiment known as the Advanced Laser Interferometer Gravitational-Wave Observatory, short Ligo. You heard a lot about it already here on SCITECHTALK Science News, which uses detectors in Hanford, Washington and Livingston, Louisiana to look for ripples in the fabric of space-time. According to the rumors, scientists on the team are in the process of writing up a paper that describes a gravitational wave signal. If such a signal exists, and it is verified, it would confirm one of the most dramatic predictions of Albert Einstein's century-old theory of general relativity. Krauss said he was for 60% confident that the rumor was true. But he said he would have to see the scientists' data before drawing any conclusions about whether the signal was genuine or not. Researchers on a large collaboration like Ligo will have any such paper internally vetted before sending it to publication and calling a press conference. In the year 2014, researchers on another US experiment called BICEP2 called a press conference to announce the discovery of gravitational waves, but others have since pointed out that the signal could be due entirely to space dust. Speaking about the Ligo team, Krauss said they will be extremely cautious. There's no reason for them to make a claim that they are not certain of. If gravitational waves have been discovered, astronomers could use them to observe the cosmos in a way that has been impossible to date. We would have a new window on the universe, Krauss said. Gravitational waves are generated in the most exotic, strange locations in nature, such as at the edge of black holes at the beginning of time. We are pretty certain they exist, but we have not been able to use them to probe the universe. Einstein predicted that the waves would be produced in extremely violent events, such as collisions between two black holes. As gravitational waves spread out, they compress and stretch space-time. The ripples could potentially be picked up by laser beams that measure minute changes in the lengths of two 4-kilometer-long pipes at the Ligo facilities. Engineers occasionally add synthetic signals to the Ligo data to test the equipment. While these are designed to mimic gravitational wave signals, Krauss said he had heard explicitly that the signal had not been added artificially. "I don't know if the rumor is solid," Krauss told The Guardian. If I don't hear anything the next 2 months, I'll conclude it was false." Gabriela Gonzalez, professor of physics and astronomy at Louisiana State University and the spokesperson for the Ligo collaboration, told The Guardian, "The Ligo instruments are still taking data today, and it takes us time to analyze, interpret and review results. So we don't have any results yet. We take pride in reviewing our results carefully before submitting them for publication, and for important results we plan to ask for our papers to be peer-reviewed before we announce the results." And that takes time too, she said. And that was Science Breaking News here on SciTechTalk Science Live channel, Wednesday, January the 13th, 2016.
Dan de planet Earth, onze planeet waar ik het net al over had. Het gerucht gaat sinds een paar dagen op internet dat er groot nieuws uit het heelal aan zit te komen. Voor het eerst zouden er namelijk zogeheten zwaartekrachtgolven gedetecteerd zijn. En als dat klopt, dan hebben we live de doodskreet van 2 samensmeltende zwarte gaten gehoord. Het gaat mij al meteen duizelen. Heel fijn dus dat NTR-wetenschapsredacteur Arnoud Jaspers is aangeschoven. Arnoud, goedemorgen.
Goedemorgen.
Wij willen er natuurlijk alles over weten. Maar dan moet je eerst even uitleggen wat nou die zwaartekrachtgolven zijn. En ook die zwarte gaten, wat dat daarmee te maken heeft.
Oké. Nou, het begint allemaal bij Einsteins relativiteitstheorie. En die zegt onder andere dat grote massa's, zoals de aarde of de zon of een ster, de ruimte om zich heen vervormen. Dus de lege ruimte, de kosmische ruimte, moet je eigenlijk voorstellen als een soort doorzichtige drillpudding. Een ster of een zwart gat heeft zoveel massa dat die pudding in zijn omgeving een klein beetje verwringt. Nou, dat is de relativiteitstheorie, dat is al lang bekend. Einstein voorspelde ook nog iets anders. Als 2 van die grote massa's heel snel om elkaar heen bewegen, dan veroorzaken ze trillingen in die kosmische drillpudding in de ruimte. En die planten zich met de lichtsnelheid voort. En die kunnen we op hele grote afstand dus ook waarnemen als ze langs de aarde komen. Die trillingen, dat noemen we zwaartekrachtsgolven. Dat effect is heel erg zwak, maar een van de weinige gebeurtenissen waarvan we de zwaartekrachtsgolven op aarde zouden kunnen detecteren, is als 2 zwarte gaten te dicht in elkaars buurt komen en dan gaan ze om elkaar heen draaien en steeds dichter om elkaar heen, totdat ze elkaar opslokken. En in die laatste paar seconden voordat ze elkaar opslokken, die zwarte gaten, zenden ze een heel sterk signaal van zwaartekrachtsgolven uit. Een doodskreet in de laatste seconde voordat ze dus elkaar opslokken, dan maken ze heel veel herrie, als het ware. Nou, en dat zouden we dus nu gedetecteerd hebben.
Daar is dus die opwinding over. En dat is dus iets wat heel kort
het duurt maar 1 of 2 seconden. En dat kunnen we ook geloof ik laten horen.
Ja, we hebben er een fragmentje van. Let op. Het is heel kort.
Ja.
Mag ik het nog een keertje horen?
Oké,
en dat is dat samensmelten.
Ja, dit is een simulatie. Hè? Dit is niet het echte signaal. Als het signaal al echt is, wat is waargenomen. Dit is een simulatie van wat daar is een grote detector voor zwaartekrachtsgolven staat in de VS. Er staat er ook een in Europa. Die heet Virgo, maar dit gaat over de detector in de VS. Ligo heet die. En die zou dus ongeveer dit horen, een signaal als dit detecteren, als dat echt gebeurd is. Ja. En dat horen is niet letterlijk hoor, maar die trilling die van die zwaartekrachtsgolf die langs de aarde komt, dat gaat met deze frequentie. En dus
dan zou je het zien uitslaan.
Ja, het is omgezet in geluid, maar het is wel ongeveer 1 op 1 omgezet in wat je dan detecteert.
Oké, en jij bent een keer bij die LIGO-detector geweest ook, toch?
Ja, ik ben daar een aantal jaar geleden op bezoek geweest. En wat je dan ziet dan zie je, dat is eigenlijk een beetje, klinkt vreemd, maar het zijn eigenlijk 2 grote kaarsrechte buizen van 4 kilometer lang. En die staan haaks op elkaar. Die zijn vacuümgezogen, die buizen. En in die buizen gaan laserstralen heen en weer tussen spiegels. En wat doen die laserstralen? Die meten extreem nauwkeurig hoe lang die buis is. Doordat dus hoe ver die spiegeltjes aan de uiteinden van die buizen van elkaar afstaan. Ja. Want wat gebeurt er namelijk als er een zwaartekrachtsgolf uit het heelal op ons afkomt en dus eigenlijk de aarde passeert, dan is het heel even zo dat de aarde, wordt van bolvormig, wordt die ietsje vervormd. De vorm van een rugbybal krijgt hij dan.
Merken wij niks van verder? Maar
nee, dat is extreem klein. Ja. Maar, en dat oscilleert ook. Dat wil zeggen, het ene moment is die iets langwerpig in de vorm in de richting van de polen. En 100ste seconde later is hij alweer langwerpig in de richting van de evenaar. Dus dat oscilleert zo. En alles wat op de aarde zich bevindt, trilt mee. Dus als die laserstralen heel nauwkeurig de afstand tussen die spiegeltjes en die buizen kunnen meten, dan zie je dat ook een heel klein beetje veranderen. En dat is die trilling die je meet. En dat zijn dus, op die manier kun je zwaartekrachtsgolven detecteren. Het is wel zo, die verandering in die afstand tussen die spiegeltjes op 4 kilometer afstand van elkaar, die verandering die is ongeveer de diameter van 1 atoomkern. Zo weinig is dat.
Ja.
En daarom is het zo ontzettend moeilijk om dat te meten.
Maar goed, dan begrijp ik niet zo goed. Ja, of het is gemeten of niet. Ik bedoel, waarom is het dan nu een gerucht?
Ja, dat is het punt. Omdat het zo extreem moeilijk is om uit die data die je hebt... want er zit heel veel ruis in. Want als er ergens een 4 kilometer verderop een vrachtauto voorbij rijdt... trilt dat ook. Dus je moet heel veel rommel uitfilteren... en dan hou je iets over... en dan moet je kunnen bewijzen dat dat een signaal uit het heelal is. Ja. Dat is heel moeilijk. Zitten ze heel lang op te analyseren, op die data... En daarom is het nu, de Ligo-organisatie zelf zegt nog niks. Die zeggen braaf, wij zijn de data aan het analyseren.
En daarom neemt die spanning nu toe? Omdat ze denken, langzamerhand...
want er zouden dus bronnen zijn, onderzoekers bij Ligo zelf... die officieel nog niks mogen zeggen, maar die al... zeg maar onder ons hebben gezegd van... joh, we hebben nou toch echt iets heel interessants gevonden.
Want die Lawrence Krauss, daar kwam een tweet van.
Ja, die heeft het gerucht de wereld ingestuurd. Lawrence Krauss is een bekende Amerikaanse natuurkundige... die nogal van publiciteit houdt. Die zit veel op Twitter en heeft een blog en zo. En die heeft gezegd dus dat hij gesproken heeft met onderzoekers... die zeggen dat ze een signaal gedetecteerd hebben... maar het is dus nog officieel. Maar... Krauss riep dat in september 2015, riep hij dat ook al. Dat was 1 week nadat die Ligo-detector een upgrade had gemaakt.
Okay.
Dus die is door modernisering is die gevoeliger geworden. Waardoor het nu te verwachten is dat hij ooit wel echt zo'n signaal uit de kosmos kan detecteren. Maar dat riep hij dus in september al, toen die upgrade net een week oud was. En toen was het dus eigenlijk nogal onwaarschijnlijk dat er al echt iets gedetecteerd was.
Dus nu heeft hij het weer over stay tuned en exciting. Maar stel nou dat het gerucht waar is, hè, dat het nu klopt. Zijn we dan klaar met onderzoek naar die zwaartekrachtsgolven?
Nee, dan staan we eigenlijk aan het begin. Kijk, die hele detectie van zwaartekracht... het is een beetje te vergelijken met... we kunnen nu naar het heelal kijken... en het is een beetje alsof we tot nu toe altijd doof geweest zijn. Dan kan je wel denken dat je ziet wat er in de wereld te koop is... maar als je dan op een gegeven moment, stel je bent altijd doof geweest... en je bent ineens niet meer doof... gaat er echt gewoon weer een wereld voor je open. Zo is het ook met die zwaartekrachtsgolven uit het heelal. Astronomen hebben dan weer een heel nieuw venster op het heelal. Ze kunnen weer hele nieuwe verschijnselen waarnemen... en ze kunnen misschien dan zelfs... zwaartekrachtsgolven detecteren die rechtstreeks van de oerknal afkomen. Dus je kunt op een hele nieuwe manier weer naar het heelal kijken of luisteren. Het is hoe je het noemen wilt, als beeldspraak. Ja. Maar er gaat een heel nieuw open dan.
Maar Einstein had wel gelijk dan?
Ja, we zijn er bijna zeker van dat die zwaartekrachtsgolven bestaan... en dat we ze ooit zullen kunnen detecteren... Maar het blijft nu dus nog even spannend of het een echt signaal is wat er gedetecteerd is.
Vandaar dus de opwinding in natuurkundig land, zeg maar, onder de natuurkundigen.
Ja.
Ik begrijp het, zomaar.
Hoe kan dat nou?
Dat was die nog een keer. Bedankt hè Arnoud, tot de volgende keer.
Ja, en dat is dan breaking news toch wel, luisteraars. Want de ontdekking van... zwaartekrachtsgolven, ja, dat zou echt een hele belangrijk element zijn. Alhoewel we er toch, de wetenschappers er toch wel van overtuigd zijn dat die algemene relativiteitstheorie van Einstein klopt. Omdat in feite alle elementen en alle voorspellingen die theorie heeft gedaan, die zijn inmiddels eigenlijk allemaal al echt bewezen. Daar is eigenlijk geen twijfel meer over. Maar ja, dit is een voorspelling die toch wel een beetje bijzonder is en ja, die niet echt triviaal waar is. Dus het zoeken naar bewijzen in de natuur dat dit allemaal zou kloppen, ja, die zijn natuurlijk wel extreem belangrijk. En daar vandaan dat we daar natuurlijk allemaal wel van willen weten hoe het zit. Tot zover dan de uitzending in verband met het breaking news over de eventuele ontdekking van zwaartekrachtsgolven. Meteen volgende op deze live uitzending van SciTechTalk Science Channel gaan we een paar documentaires bekijken die al veel eerder hier op SciTechTalk waren te zien, maar die nou natuurlijk veel actualiteitswaarde krijgen. En die gaan allemaal over dat LIGO. En ik moet eventjes voor me kijken om te zien wat het ook alweer betekende. LIGO staat voor Laser Interferometer Gravitational-Wave Observatory. En daar is tegenwoordig een geavanceerde versie van en die heet Advanced Laser Interferometer Gravitational-Wave Observatory. Dat zou dan Ligo zijn. En die gebruikt detectoren die staan in Hanford in Washington in de Verenigde Staten en Livingston, Louisiana. En die zoeken eigenlijk naar rimpeltjes in de fabric of spacetime, de textiel zeg maar, waaruit onze ruimtetijd waarin wij leven zou zijn opgebouwd. Bedankt voor uw belangstelling. Voor de kijkers op het YouTube-kanaal, die kunnen dus direct gaan kijken naar heel uitgebreide documentaires over die detectoren en wat houdt dat nou allemaal precies in. Dat LIGO-systeem, waarmee het instrumentarium, waarmee men probeert te meten of die zwaartekrachtsgolven bestaan. Een extreem moeilijk natuurkunde-experiment is dat.
It's a pleasure for me to be here, and I'm honored to have been invited to share with you all some information about what we think is going to be a fantastic new tool for astronomy. That's the Advanced LIGO project that I'm going to tell you about. And one of the most amazing things, as you can see from my title, is that we'll be able to learn new things about black holes by literally listening in on them as they spin around each other, collide, and vibrate. So black holes, I don't need to tell anyone in this room, are fascinating objects and enigmatic objects as well. We would dearly love to know a lot more about them. What I'm projecting here is a still that in a little bit is going to turn into a movie. This is an image of the very center of our own galaxy, taken with adaptive optics infrared imaging by Andrea Gez's group at UCLA. And it turned into a movie while we were talking. We'll look at it again in a moment. You see a bunch of stars, the colored spots, and as time elapses, you can see in the upper left, from 1995 up to the stop at 2010 when this animation was pulled together, the stars in their original positions shifted. Okay, stars have proper motions, that's fine, but they seem to be shifting under the influence of a whole lot of mass marked by that five-pointed star in the middle that's been drawn onto the images because there's no light coming from that spot. And in particular, there's a couple of stars that you can see, if we watch the movie one more time, that actually make complete elliptical orbits around that spot where there's no light coming from it. And because we understand gravity, we know that if something goes around a spot, there must be mass there. Furthermore, by measuring the size of the orbit and the period of the orbit, we know how much mass is there, and that's millions of solar masses sitting at the center of the galaxy emitting no light at all. So even though I'm using units of solar masses, there's nothing like the sun there. And we're pretty darn sure that that's a massive black hole. Here is one of my favorite images in astronomy. It illustrates another thing that we think is a black hole. This is the irregular galaxy Centaurus A, and many of us are familiar with the optical image of this unusual galaxy. Here's a small version of that. These are four different views that are put together in a false color composite up here. So here is the classic view of this galaxy. Looks sort of like an elliptical, but sort of like a spiral. You can see a dust lane. There's another indication that it's something like a spiral. Here's a 21 centimeter radio map of that galaxy. There's clearly a disk of cold gas. But we've also got other radio observations that show there's jets. Here's the Chandra X-ray image of this object, showing that there's a lot of hot gas. And look, Sure enough, there's a jet there, and clearly there's some jets feeding those radio lobes, and some hints of a spot there. Probably, almost surely, a black hole. But what do we know about that black hole, or the black hole at the center of our own galaxy? Not nearly as much as we'd like. So what I would like to do now is talk about the next frontier in learning about black holes. And while we're on our way, we'll also be building yet another element of this fantastic feature of astronomy in the last 50 or 60 years, namely multi-messenger astronomy, not just looking with light, but as illustrated in this slide, across the whole electromagnetic spectrum. What I'm going to tell you about now steps outside the electromagnetic spectrum entirely, a whole new messenger for astronomy, and that's gravitational waves. So before I tell you what a gravitational wave is, I'm going to give you one more teaser, and that's to give you an indication of what kinds of things this new technique for looking at the sky can tell us. What is illustrated on this slide right now, this is the first still image of another film I'm about to show you. We have two black holes in orbit around each other. This is a supercomputer simulation of what will happen when two black holes orbit around each other, made at Goddard Space Flight Center a few years ago. And you can see the black holes going around each other, getting closer and closer. And note this red character to the space around them that's being illustrated. And you saw something illustrated by red in a supercomputer visualization animation was being sent out from that pair of black holes that now have turned into one black hole, about as big as the two original ones were. But in that process of their last couple dozen orbits around each other, they spiraled towards each other, did something important to space that's going to be a key to how we can observe this, and then turned into one even more massive black hole. The red marks that were there in that animation are the distortions of space-time that we call gravitational waves. And they are the messengers by which we are going to be able to learn more about black holes, and in addition, learn about many other interesting kinds of objects in the sky as well. So when people ask me what a gravitational wave is, the simplest analogy I can give is that they are vibrations of space-time, disturbances in the structure of space-time that propagate through space like ripples on a pond when you throw a rock into it. They are in many ways like other kinds of waves that we're familiar with. In some ways, they're very much like sound waves. And that's actually kind of remarkable. I'm going to be building up this analogy for you, but think of it as vibrations in the audio spectrum that propagate out through the speed of light, out through space from a disturbance at the speed of light. They are this much like sound waves, at least. The ones that the Advanced LIGO project is going to be listening for are in fact in the human audio range. And some of you, I recognize a few of you who stopped by the Montclair State LIGO booth out on the exhibit floor, and we had set up there a computer program that was playing back calculated gravitational waveforms from various kinds of binary star systems coalescing and emitting gravitational waves. And we just put those calculations, played them through speakers, and you could hear various kinds of whoop. There was no speed up, no audio processing whatsoever. Those weren't recorded gravitational waves yet, they're predicted ones. But we're very much hoping to hear signals quite like that in the near future. When we find them, we'll find not only black hole binaries like what you saw, but binaries of neutron stars. We hope to find signals from the stellar core collapse that ignites a supernova, and we hope many other phenomena as well. Now, gravitational waves, as I said, are signals that we have not yet received. But we do indeed have good experimental evidence that the phenomenon of emission of gravitational waves by a binary system does exist and does obey the theoretical prediction that comes from Einstein's general theory of relativity, our best theory of gravity. And on this slide, I'm illustrating that evidence. In a moment, I'll explain this graph that contains the evidence, but first, let me set the stage. In 1974, the radio astronomer Joseph Taylor and his student Russell Hulse were observing at Arecibo, trying to find as many pulsars as they could. Pulsars, of course, are neutron stars spinning on their axis, and some of those neutron stars that spin on their axis sweep a beam of radio waves past us every time they turn. And since pulsars can turn several times a second, many times a second, we see repeated radio pulsars and hence their radio pulses, and hence their name, pulsars. This particular pulsar that we're going to talk about, 1913 plus 16, astronomical names are so evocative, aren't they? Was clearly unusual in that the pulses didn't seem to be coming in quite the steady pattern that was expected. Over the course of the night, Hulse and Taylor realized that the pulse arrival rate was being modulated by the fact that this pulsar was in orbit in a binary system. And as succeeding years let them refine their observations, it became clear that what we had were actually two neutron stars, one visible in radio wavelengths as a pulsar, and the other also a 1.4 solar mass object, formerly a star, now all collapsed down to something just the size of a small city, entirely made of neutron matter. Hulse and Taylor realized that this was tailor-made, sorry for the pun, to test Einstein's prediction that binary star systems were emitters of gravitational waves. It's not a very hard problem in the graduate school course that you take on general relativity to calculate how much energy should come from a pair of stars of known mass in a particular orbit. And they did that calculation and made a prediction that as the years would go by, the orbit of these two stars would get ahead of itself by the loss of energy, the stars falling closer together, and the orbit speeding up, so that over the course of the succeeding decades, they expected eventually the two stars to come around to a given spot in their orbit as much as 30 or 35 seconds early. And then they set about observing year after year, and the red points are what lies on, are what shows what the star system actually did, and you see they fall right on the predicted line. That says that that binary system is losing energy at precisely the rate that Einstein told us would happen if that binary system launched into space vibrations just like those red marks in that animation that I showed you of a black hole binary. And so you can see that the data lines up on the theory perfectly. The agreement is better than 1%. And this was such a fabulous discovery that it earned Hulse and Taylor the Nobel Prize for this discovery. And this gives us confidence that, in fact, the theory of general relativity is telling us the truth when it says that anytime you've got two stars orbiting each other, they are going to emit energy in the form of gravitational waves. And indeed, anything that rotates in a way that is out of round, that is somehow lumpy, not axisymmetric, as we say, is going to emit gravitational waves as well at rates that we can calculate so long as we know to what extent that system is not symmetric about its rotation axis. This means that there's a chance, if we build the right kind of devices, that not only can we see that energy is quasi-mysteriously being lost, Not too mysterious because we know why, but we can actually observe the effect that's carrying away the energy, that is, detect the gravitational waves themselves. So now let me sketch for you how one could invent a gravitational wave telescope. And then after I've explained the theory, I'm going to show you the actual gravitational wave telescope that we've been building and that we hope will successfully observe gravitational waves sometime in the next few years. So first we're going to start at the thought experiment level. I want to ask you to imagine that you have the power to set up this very simple to describe but kind of hard to do in practice experiment. On the screen, I'm showing you 8 red dots, and you should imagine each of those dots to represent an object. From now on, I'll be calling it a test mass. What I mean by a test mass is some object with some mass, that means it could be made of anything, because everything has mass, placed in a situation where there are no forces on it at all. At least no forces other than possibly gravitational forces. So imagine going out in space, you're on the next shuttle mission and you go out and you plant this ring of 8 masses that then are just supposed to sit there and float and do nothing at all. If into that apparatus of that thought experiment, a gravitational wave should propagate into the plane of that circle that those masses have been placed in, this is what will happen. If an oscillatory gravitational wave is passing through the plane of that thought experiment apparatus, what it's going to do is to distort the relative positions of those masses. It's going to alternately tug and push in the x and y directions in antiphase, as you see. At moments when that circle is stretched extra left to right, it's shorter top to bottom. And in moments when it's taller top to bottom, it's squeezed left to right. So a gravitational wave, according to our understanding of it, will cause relative motions in sets of test masses that are free to move in this characteristic pattern. And all we have to do is figure out how to see it. Now, let me say a bit more about that pattern and point out some features that will help you see how we've invented an actual working detector. So now I've made a more crowded drawing, but it's not going to move. In this drawing, can you see a red spot? Okay, there we go. In this red drawing, each square represents a test mass, and I put them in a more crowded rectangular grid so that you can see more features of the pattern. Now, because I'm not showing a movie, I wanted to show you 2 stills. And the 2 stills are the following. And the original perfectly regular square array is marked by the empty squares. And then a gravitational wave comes by and we're catching it at some instant, and at that instant the positions of the various test masses are marked by the filled squares. And you can see, if you stare at it for a little bit, that we've caught it at a moment when, in the left-right direction, all the distances are stretched, and at that's also an instant where in the up-down direction, the distances are compressed. Okay, so we can see it maybe more clearly here, maybe the circle's better, I'm not sure. But now let me point out something else. If you ask the question, how far apart have any 2 test masses moved at that instant? If you compare the positions of 2 masses that are near each other, they've moved a little bit. And it doesn't matter which pair you pick, they've moved by a little bit. If, on the other hand, you compare how much, say, this one has moved compared with this one, it's moved by a lot more. And in fact, the distortion is of a character that the relative motion between any 2 objects is proportional to how far apart they started. We call this a strain pattern. And in fact, this is the thing that characterizes the influence of any given gravitational wave on an apparatus. It is the measure that we use to describe the strength of a gravitational wave. I may sometimes refer to it by the letter little h. That's the traditional symbol we use. If I ever do, I'm just telling you something that is the fractional separation change divided by the original separation change. Traditionally, we multiply it by factors of 2 that don't need to concern us. So, this fractional length change, this strain, is the characteristic effect of a gravitational wave. That means that if we want to see the effect and we're only going to have a few test masses, what we'd really like to do is park them pretty far apart to make the biggest effect possible. Now, gravitational waves don't have to be simple sinusoidal waves like I showed you in the movie 2 slides ago. They can, depending on what is emitting them, have really interesting shapes. And this is a particularly interesting shape that comes from the very end of the orbit of a binary system. This is 2 black holes that are orbiting. Here's their last orbit or so, and boom, now they have set up some vibrations in the new joint black hole that formed when the 2 went clump together. And that's, in fact, what this sound would be, something like a clump. So when we're able to detect gravitational waves, we will be studying not just did we see it and what was the frequency, but hopefully the evolution of the frequency will carry information about what happened in, was it a binary, was it a stellar core collapse, was it who knows what, that emitted the gravitational waves. The gravitational wave form that we can read out by measuring the history of how far did these masses move one way, then the other, one way, then the other, and then it died away. Okay, if we can measure that, we can interpret what we saw in terms of what happened to the source. Now, I said a moment ago that these are happening in the audio band, and I'd like to play for you all a few recordings of actual expected gravitational wave signals from binaries. So, my helper in the back, if you can cue the first sound, this sound is going to take a little bit of time to cue up because binaries, what's the odd thing about everything I've told you? Something should be upsetting you. Something is strange about the physics that I'm using to describe this. When we talk about binary star systems normally, we assume that they're stable. They shouldn't be evolving at all. It's only when they get very close together that their orbit is fast enough around each other that they emit enough gravitational radiation to become noticeably unstable, and then it's a runaway process because the more energy they emit, the closer they get to each other, the faster they go around, the more energy they emit, the more they fall together, the faster they go. And that's why whenever you get gravitational waves from a binary system, you expect a humongously long period of inaudible emission of weak gravitational waves, followed by, in this case, not that many seconds of finally audible in the base range, but sweeping up as the orbit speeds up. And finally, the loudest moment is the highest bloop at the very last instant. Okay? Now, that particular calculation was for the gravitational waves expected from a pair of neutron stars, kind of like the Hulse-Taylor pulsar 1913 plus 16. I've got another recording that will go much more quickly when we play it. Let's play it. That's a couple of 10 or 15 solar mass black holes going into each other. Sweeps very quickly from the inaudible frequencies up to the final frequency. So you can see that another way to efficiently emit gravitational wave energy is to start with more mass. That makes the evolution quicker. So when we find a signal like this, we will know we were right about how gravitational waves work, but we'll also be able to read off the combination of masses that made it. And if there's other interesting physics going on, such as if one or both of those black holes happen to have a lot of angular momentum, a lot of spin, there would be some modification to that signal that we could read off as well. So it's a tremendous probe of stuff that's going on in an invisible sector of the universe. And the very last moments of these waveforms may contain rather dramatic clues, not to the physics of orbits, because until the very end, we still have two individual objects orbiting around each other. But at the very last moment, there's some sort of coalescence event. Two neutron stars crash into each other, two black holes crash into each other. That's a really interesting thing. That's kind of hard to calculate, but will tell us a tremendous amount about the dynamics of putting together a black hole out of two black hole pieces, or putting together a black hole out of two neutron star pieces. And we are really excited to be able to eventually study those last moments of gravitational wave signals. Of course, for now, we'll be happy to catch any of these gravitational wave signals. It's going to be a tremendous moment when that happens. Now, gravitational waves are such a different kind of information carrier or messenger that it's hard to imagine that they won't give us a really new view of the universe. They are as guaranteed as anything is predicted by 20th or 21st century physics that we haven't yet seen. The reason we expect them is that they are gravity's obedience to Einstein's principle that no information can travel faster than light. And so if Einstein was right about anything, he must have been right about this. This is the bedrock of all of relativity theory. Given that, we expect them to be made most strongly, as I've indicated, whenever large masses move in accelerated motions at relativistic speeds. They will travel through opaque matter. They can be generated by things that aren't even really stuff. Black holes we sometimes describe in physics as being made out of pure space-time. They're not made of atoms or the like. So we expect these signals from black holes. We expect them from fluctuations in the very early universe, being able to peer back much, much deeper towards the Big Bang than the cosmic background radiation, which has taught us over the last few decades so much about the history of the Big Bang. So when we are finally, in a few years, in the business of finding signals from gravitational waves with the advanced Ligo detectors and a few others that I'll tell you about, we do indeed expect to find signals from binary systems that I've been illustrating of neutron stars and of black holes. When we do, we'll be learning about the details of black hole dynamics in a way that no other astronomical tool that anyone has thought of will enable us to do. We'll be able to learn about the internal forces between neutrons that determine the structure of neutron stars. We expect that it's quite likely that the detection of gravitational waves from neutron star binaries will allow us finally to understand the mechanism that generates gamma ray bursts, this very enigmatic signal that's been puzzling us since the mid-70s. Eventually, we hope to see gravitational waves from the collapse of the core of a massive star that, with very good reason, we believe to be the initiating event of type 2 supernovae. But we will be able to observe that and understand the dynamics of that event and what leads to the supernova phenomenon. We think it's quite possible we'll also be able to study individual rotating neutron stars, in effect kind of gravitational pulsars, if those neutron stars are sufficiently out of round as they rotate. And as I mentioned briefly before, there's a reason to hope that we will eventually find signals from the very early universe, a gravitational background that's analogous to the cosmic microwave background, except coming not from 300,000 years after the Big Bang, but from the tiniest sliver of a second after the Big Bang. So, once this technology is operating, we think it should be fabulously fruitful as a tool for astronomy and even cosmology. So, I hope I sold you on the interest of gravitational wave detection, but there's still the small matter of inventing a gravitational wave detector and making it work sufficiently well to actually fulfill all these promises. So, let's sketch out how we would move from that thought experiment in the direction of a real experiment that has a chance of working. So as I illustrated in the thought experiment description, we need a set of test masses as far apart as we can practically make them. They should be free to respond to this gravitational influence. We need some way of measuring their relative motion, and which you want to think about because we're not talking about putting things right next to each other. We're trying to make them far apart. So we need some distance measuring system that will work for far apart test masses. And we need something to take the place of the science fiction version of the experiment where I said, let's just have some astronauts lean out the space shuttle and drop masses in a circle. We need to have these masses in a situation where they are isolated from other causes of motion. Now, to give you a sense of why this might be a challenge and why, even though Einstein predicted these waves 99 years ago, why I'm here today telling you we think we're about to succeed in a couple of years. Okay? And now here is the reason. When we finish those calculations of two black holes orbiting each other, or two neutron stars orbiting each other, as in pulsar 1913 plus 16, and we say, okay, how strong are the gravitational waves going to be once they reach us here at Earth? We find a rather disturbing answer. We see that the separations between masses are going to change from their original separations, not at like the part in 20 that I showed you in that diagram, not a part in 1,000, not a part in 1,000,000, not a part in 1,000,000,000, but by about a part in 10 to the 22. And if that number isn't scary, if you like numbers with dimensions rather than numbers that are dimensionless, let me skip ahead and tell you that the instrument I'm going to describe to you in a little bit, Advanced LIGO, has its test masses separated by 4 kilometers. 1 part in 10 to the 22 means relative motions of mirrors at the two ends of each of LIGO's 4-kilometer arms of less than 10 to the minus 19 meters. I sense a silence falling over the room. How small is 10 to the minus 19 meters? Well, here are a few small things. The diameter of a human hair, 10 micrometers. The diameter of an atom, 10 to the minus 10 meters. The diameter of a typical atomic nucleus, 10 to the minus 14 meters. The diameter of a proton, 10 to the minus 15 meters. So, I'm here to tell you that we know how to measure relative motions of chunks of glass by a displacement that is 1/10,000th the diameter of a proton. And that is required if we are going to successfully detect gravitational waves. Okay, but we can do it. Now, let's, with this challenge in mind, see how to actually make a practical gravitational wave detector. So, I've taken that crowded diagram from a few slides ago with all those squares, and now I've said, let's just think about 3 test masses, say, and pick them out in an L shape to capture the fact that we've got this interesting symmetry to our effect that every time something stretches along what I can call the x direction, there's a compression along y, and vice versa. And that's suggested by the open squares representing the original positions of the masses and the closed filled squares, the instantaneously moved ones. But remember, now this diagram contains the big lie. If I drew it to scale, it wouldn't explain anything because you couldn't see what was going on. So I've had to dramatically exaggerate the effect just to make it visible in this room. Now, as I said, we put ours 4 kilometers apart. It's about as much as you American taxpayers were able to cough up. We're extremely grateful to the fact that over the past couple of decades, a good fraction of $1 billion has gone into this initiative. And so with all humility, I say thank you. I think this is an audience that I don't have to work too hard to convince that your fraction of $1 billion, you know, each household in this room contributed $5 or $10, okay? Not negligible. We're hoping to give you your money's worth. Now, I still have to tell you how you can measure the relative motions of a set of test masses like that, and then convince you that it has a prayer of working at the required sensitivity. What I'm showing on this slide is a diagram of an instrument that many people in this room have learned about. This is one of the classic experiments of, I was going to say 20th century physics, but it's actually 1887 when Michelson and Morley used a device very much like this to look for what they thought was some slam dunk physics based on the very best understanding of the universe at the close of the 19th century when we understood everything. I'm talking, of course, about the motion of the Earth through the ether. So this has now come to be called a Michelson interferometer. It consists of not many parts, so let's walk our way through it. There's a source of light. We'll use a laser. Michelson didn't have a laser. A beam-splitting mirror, which is a mirror that is partially silvered at that time, or with fancier coatings now, chosen so that about half, or in our case very precisely half, of the light power is transmitted through it, where the other half is reflected and turned, if you orient things correctly, in a perpendicular path to the original beam. Then, some distance away, Michelson had a big granite table. We have 4 kilometers of desert in one place and forest land in another place. You put a mirror at the end of each of those 2 perpendicular arms. The mirror sends light that was originally sent from the light source, split at the beam splitter, traveled down the 2 perpendicular arms, sends it back in the direction of the beam splitter. Things are aligned right. The 2 beams of light superpose. And then you can look with your eye, if you were Michelson, or with a photodetector today with brighter light sources, at those 2 superposed beams that have done something slightly different. One of them moved in this direction and back. The other beam moved in this direction and back. Michelson and Morley expected that one of those beams would have taken a little extra time compared to the other because light traveled at the speed c with respect to the ether through which the Earth was moving. So went the theory. Okay? And the theory was well posed enough that Michelson and Morley knew exactly the size of the signal that they were looking for. And when they set up this apparatus and did not see it, that was the most amazing failed experiment ever. Okay? We're supposed to say no experiment is a failure if you do it correctly. Getting the wrong answer can be much more interesting than getting the right answer. And this is surely an illustration of that, one of the greatest failed experiments ever in the history of science. It led some decades later and to Einstein's postulation of first the special theory of relativity in 1905, and then in 1915, 100 years ago this year, the general theory of relativity, that includes our understanding of gravitation. Now, how is it that a Michelson interferometer lets you see whether things have gone slower in one arm than in the other? Here's an illustration. I want to talk about 3 different cases. In the middle of the slide, I'm showing you what your eye, if it's safe, or a photodetector, if there's too much light, would see looking up at the beam splitter in 3 different cases. And in 3 different cases, you either see bright, medium, or dark. Here are the 3 cases. In one case, the light waves have taken precisely the same amount of time to go down the arm and back and come back to the beam splitter. In that case, the wave crests and troughs of the electric fields in those light waves are lined up, and when you superpose those 2 beams, you get constructive interference and see the brightest possible beam. You see something as bright as the original light source was. If instead one arm was slower than the other, the 2 light beams won't arrive back in phase. If the slowness is such that one light wave arrives 1/2 period of its oscillation, and remember, visible light has very, very high frequency of oscillation, over 10 to the 15 hertz. So this is a very tiny measurement of time delay. But if the delay is sufficient that the waves actually arrive completely out of phase, crest lined up with trough, trough lined up with crest, you get completely destructive interference, and no light will come out of that port of the interferometer. If it's been an intermediate amount of time difference, you'll see an intermediate amount of light. So, by measuring the brightness of the light that emerges from the beam splitter of the interferometer, you can tell whether the light waves have taken precisely the same amount of time, or if not, you can make a pretty precise measurement of how much different is the travel time down the 2 arms. And that's sounding like what we want. Here is a diagram from Michelson and Morley's 1887 paper illustrating the apparatus. And you can see this big granite table. They mounted it on a huge mercury bearing. It would never pass OSHA regulations, the amount of mercury they had sitting there, to allow them to very gently rotate the apparatus so that they could exchange the role of the fast arm and the slow arm. And in that's actually how they spotted the signal. When you first set this up, it's really hard to know you've set up the 2 arms precisely the same length, but this way it doesn't matter. You can set them up close and then turn it, and you'll see the slowing and speeding alternately in the 2 arms and get a signal. So let's do a tiny bit more of a tour of this apparatus. There's a beam splitting mirror there. There's another thing that looks a lot like it in one of the arms. That's a compensation plate. I can explain that in the questions if you want to know why there's a compensation plate. From this corner is where the light was injected from a carbon arc lamp. And the light was split, some going this direction, some going this direction. Now, notice that you don't just see one mirror at each corner. There's 4 of them. And in fact, there's some more over here as well. And in fact, some that you can't see here. That's because when Michelson first did this experiment in 1880, it was a pretty good experiment, except when he finished analyzing the data, he realized he didn't have the sensitivity to see the predicted effect. And because his arms weren't long enough, given how finely he could compare were the waves precisely superposed or not. So what he did, he couldn't afford a bigger table, but he said, I'll make the light travel a longer path by snaking its way in this arm back and forth this way, snaking its way back and forth this way for multiple round trips. And When he did that, he got the sensitivity so that when he saw nothing, he knew he should have seen something. And so that's why we refer to the Michelson-Morley experiment. It was Morley, who was his assistant, who came on and designed this beam folding system, as we call it. Now, we aren't going to have the luxury of doing something that was really important to Michelson. If you look carefully at this diagram, hand-drawn lovingly for this 1887 article, you'll notice that the mirrors are mounted on what must be, as rigid as 1887 technology could provide, adjustable mounts, so that the vibrations in the laboratory wouldn't disturb the positions of the mirrors and thus give a confounding noise hiding the signal. So they had to be very rigid but adjustable so that the mirrors could be put at the right angle so that the light would snake its way the right way and then make it back to the beam splitter and have those two perpendicular beams superposed. We can't do that. We need something that is going to fulfill that idea in the thought experiment, be able to respond to a very weak gravitational force. So we have to have our mirrors, to as good an approximation as we can, be free to move. Now, if they're really free, they would fall down and break. And neither we nor the taxpayers would like that. So we've got a near approximation to freedom. We hang our mirrors from very fine wires as pendulums. And of course, in vertical direction, you hope a pendulum is rigid so the mirror doesn't fall to the floor and break. But in the horizontal direction, for any influence that goes back and forth at a rate faster than the swinging frequency, the resonant frequency of the pendulum, the motion of that mirror is as if it were free. So if we know we're going to start looking for gravitational waves at frequencies above 10 hertz, say, as advanced LIGO will, for this purpose we just have to ensure that the resonant frequency of the pendulum is at a frequency that is low compared to 10 hertz. And a pendulum this long has a resonant frequency of about 1 hertz, so we're golden. We've got free masses. Now, that means that we've got a challenge that Michelson solved by machining those remarkably rigid adjustable mounts. We've got to somehow figure out how to put these mirrors in the right place and aim them the right way without actually holding them in place. And we do this with a marvelous engineering technology called feedback control. And I could give you a whole other lecture for the engineers in the room about our amazing feedback system. I won't do that, even though I'm tempted to nerd out on you all. But let me just say, it's an amazing feat of 20th and 21st century technology all on its own. Now, we get another benefit from suspending our mirrors as pendulums, and that is where there was this other rather remarkable requirement that we need our mirrors to be isolated from any non-gravitational influence from the nearby environment that might cause a confounding noise. And a pendulum is a good way to do it. For frequencies of disturbance that are high compared with the resonant frequency, they're pretty good isolators. So we get two benefits for the part of one. Now, that's not nearly enough. And I'm sketching for you something that indicates something I'll show you in some more detail in a moment. We actually need, in effect, 4, 5, 6, 7 stages of pendulum isolation in order to succeed. The motion of the ground on which we walk vibrates by about 10 times more, 10 orders of magnitude, that is to say, more than the motion we expect from a gravitational wave. So we need a rather remarkable degree, 10 to the 10 billion, factor of 10 billion of isolation from vibrations of the ground. So our motto is isolate, isolate, isolate. I'll say more about how we do it in a few minutes. Now, we're ready to transition to the actual apparatus. And here are aerial views, only way you can get a good view of the whole thing, of the two elements of the LIGO project's interferometers. Here is one 4-kilometer long interferometer on the Hanford Nuclear Reservation in southeastern Washington State. And here, a near twin installed in the pine forest of southeastern Louisiana in the town of Livingston. These were completed and put into service for a first round of observations that we call initial LIGO in 2005, and with a few interruptions for small upgrades, observed, listened to space-time until 2010. So we got 2 years of operation in those 5 years when both were on at the same time, working at their design sensitivity. So that was a tremendous achievement in moving from thought experiment to practical system. We have partners in Europe. We have a very close working relationship with a project in the UK and Germany called GEO. They have a 600-meter interferometer that you can see in this field near Hanover. And we have also very good working relationships with an Italian-French team called Virgo, and they have a 3-kilometer interferometer near Pisa. And both of those instruments went on the air at the same time as we did, and we analyzed our data together in our search for gravitational waves. A little bit more about our hardware. Here's the construction of one of those 4-kilometer arms. This is, I think, the Y arm at Livingston, Louisiana. The light has to be in a very highly evacuated space. If there were anything like room pressure of air, the fluctuations in density of air along those 4 kilometers would cause way too big a change in travel time for the light. So we've made a meter diameter by 4-kilometer long in each arm vacuum pipe that's evacuated to a pretty good vacuum, 10 to the minus 8 torr. And this was put together all 16 kilometers at the 2 LIGO sites without a leak in the field. And here's a moment when a new section has just been added on, a weld has been made, and the concrete cover is not yet put over the top. Here is, inside the corner building at Livingston, a vacuum tank, pretty big one that holds a beam splitter. I'm about that tall. So you get a sense of the size of these things. And some other vacuum chambers holding some of the other mirrors that make a practical interferometer work. And you can see this is pretty beautiful high bay space with a wonderful crane for picking up and dropping down various parts of those very massive vacuum tanks while we're installing them and while we're installing the parts. So here is our new 200-watt laser for our new upgrade, the one I'm going to tell you about in a moment, called Advanced LIGO. We need a lot of light to do the interference measurement precisely. In order to tell how precisely bright we are, which is how we know where we are to 10 to the minus 19 meters, we need to start with a lot of light from the laser. And this is a brand new custom-built 200-watt neodymium YAG laser designed by our German colleagues at the Laserzentrum Hanover. Here's a little bit more about our vibration isolation system. Here is our final test mass, our mirror. It's suspended by very fine wires from another object very much like it, another cylinder of glass. That in turn is suspended by fine wires from a set of metal springs, which in turn are suspended by more wires from more metal springs on up. 4 good stages of vibration isolation. There it is in the CAD drawing, and here is a photograph of the test mass itself with the pink. That is what our human eyes see in for a high reflectivity mirror at neodymium YAG wavelengths. Here's the assembly of the pendulum. The wires are actually made out of fine fibers of fused silica, welded in place in very clean conditions. Here is a bit more about our vibration isolation. Not only do we use all those stages of pendulums, but we have 2 stages of feedback control, low frequency isolation systems. These are another fantastic example of feedback control engineering that I don't have time to tell you all about. Now, we ran, as I said, between 2005 and 2010 in an instrument that we called Initial LIGO, and I'm sorry to have to report that we didn't find any gravitational waves. We were disappointed, but not surprised. We had every reason to think that we didn't have quite enough sensitivity with Initial LIGO. We could see neutron star binaries, our fiducial source, whose strength we know very well, out to about 20 megaparsecs with Initial LIGO, but we had every reason to think it was going to take 200 megaparsecs range to see it. The instrument I'm about to proudly announce, Advanced LIGO, will see to 200 megaparsecs, and therefore we expect we're going to see these signals. So here's this diagram. Study it well. This blue sphere with a radius that extends out to the Virgo cluster is how far Initial LIGO can see. Let's go right ahead. Let's get past this. Here it is again. Now, in this diagram, that big sphere is just this tiny one. Advanced LIGO, that is about to turn on, can see 10 times farther away, which means a volume 1,000 times as great. And that volume is big enough to contain neutron star binaries that we will see multiple times per year. We're tuning up Advanced LIGO as we speak. This is a display from the control room that I grabbed from about a week ago, and you can see that the Livingston interferometer is now seeing as much as 60 megaparsec range for neutron star binaries. That's already 3 times as far as Initial LIGO. And because it's working so well, we're going to start our first observing run this September. Over the course of the next few years, by something around 2018 or 2019, we expect to hit our 200 megaparsec target range. And sometime between this fall and then, we will be finding neutron star binaries, black hole binaries, and who knows what other surprises may turn up. So we're expecting to go from technology development to astronomical tool sometime in the next few years. Within a year, Advanced Virgo is going to turn on, again at about the same kind of improvement in sensitivity. Within a few years after that, a 3rd LIGO detector in India will be installed. And then we will have the stereophonic to start with and eventually quadraphonic way of telling where things are on the sky. Because just like a single ear isn't very good at telling where a sound comes from, a single gravity wave detector is not good at all telling where a gravity wave comes from. But once we have 2 or more, we start getting information on where things are on the sky. So this global network is coming along just in time. Now, you can, and for many good purposes, you should not just build gravity wave detectors on the ground at the size you can afford to put them on the ground. This is a schematic diagram of a proposal for a gravity wave detector in space called LISA. It is something very far along in the planning stages. It has not made it to the top of NASA's priority list, something of great pain to us. We know NASA does other good things. We nevertheless thought this was a wonderful idea. Our colleagues in the European Space Agency are still planning to put together a version of this sometime in a decade or 2 into the future, and we hope they get a lot of help from NASA. And this is an indication that there's lots of science yet to come. There's a whole spectrum, just like there's a whole spectrum of electromagnetic waves, a whole spectrum of gravitational waves that a variety of new experiments can explore. We think it's going to be a wonderful period of time for astronomy. We hope that you share our excitement and are looking forward to hearing our results in a few years. Thank you very much for your attention.